Hello, everyone. My name is Yaron. I'm going to present this time online on this topic of how to essentially extend Kubeflow, which is the machine learning framework on top of Kubernetes, how to extend it and simplify it using serverless technologies and make it scalable and easy. So first, a few words on myself. I'm Yaron. I'm CTO and co-founder for a company called Iguazio. We're delivering automated data science platform oriented towards production based on Kubernetes and also incorporates Kubeflow as part of it. So before I talk about Kubeflow and serverless, and let's examine what are the real challenges that we're trying to tackle. So today, what you see in most organizations, machine learning is still pretty much in the research environment. People take a few CSV files, Excel spreadsheets, they upload some data, run a notebook or Jupyter or something like that, run some analysis on the data. And based on that, they run some training and generate models, in some cases taking those models and put them behind an HTTP endpoint and serving those. The challenge is really when you're going to a real application. Think about applications do fraud detection, real-time recommendations, things that do predictive maintenance, etc. Those are real pipelines, and machine learning is just a component within this pipeline, and also needs to perform fast in reasonable performance with high availability and scalability, and all the attributes of a production system. So what we see is that the need to move from this research environment to a stack where you have real-time ingestion from a variety of sources, whether it's through ETL process from operational databases, streaming data from transaction feeds, logs, etc., integrating with external API, which may extend our data set quite a bit, pushing it all into an analytics engine. This analytic engine does data preparation at scale, usually on a lot more data than what you would build in your own notebook, sometimes terabytes of data versus few gigabytes on an in-memory notebook. Once you've done that, you need an automated system to run various experiments, training with different sets of parameters, with different algorithms, referring to it as sort of AutoML. And those things generate machine learning models that are served using real-time interactive microservices. And those microservices may get evented through HTTP or through streaming like Kafka or Kinesis, etc. But they also need to get some real data that is very much aligned with the data we use for training. So we need data preparation also for the productization part, for the serving part. And once we've done that, we also need a monitoring, essentially a feedback loop to monitor our models, detect drift in our model behavior, and sometimes do automated retraining or formation of ensembles, changing weights and other things to mitigate loss of accuracy in our models. Now, the main challenge is today that those are usually two different departments in an organization. There's one group that builds data science products or models. There's a different group that tries to productize all of that, and that in many cases involve refactoring the entire set of code, and project takes forever. According to analysts, more than 80% of the project just fail flat due to this transition of essentially rewriting everything, recomposing it, taking Python code, changing it to Spark and Scala, sometimes moving code to C and Go to make it higher performance, and using different paradigms. So that's one of the major challenges that we need to address. Now, if you think about what is the basic element is that data scientists write their code in a notebook. And in many cases, they take their code and they create very long notebooks that comprise of different steps in the workflow, like writing a single sanction that reads some data, and then some things that generate charts, and some things that generate a training set, and then running some validation, all within the same jumbo notebook, and finally running some serving within the notebook. So the first thing we need to think about is how to transform those notebooks into microservices that we can later use as part of a Kubeflow pipeline or an orchestrated workflow. And that's the first challenge. And that may involve some work also on the data scientist part to break down his code to modular functional building blocks. But that's the first thing that we need to think about. And once we were thinking, okay, we've created this piece of code that needs to go into production as a training logic or a feature preparation logic or ensemble logic, etc. Those are all the steps that it needs to go through, from just having a Python code to having a production-worthy microservice that's automated in production. So, for example, we need to take the code and add dependencies and packages to it and build a Docker container out of our code with run scripts and parameters and arguments and all of that, which are not intuitive for too many data scientists. The next thing, which is very challenging, is how do we take a code that runs on a single process, single container, and we distribute that because we have a lot more load, more data, or a bigger computation problem to solve. We want to leverage the benefits of Kubernetes, of scaling out resources, to essentially break that piece of code into smaller pieces that work in concert to generate to address a bigger workload. So in many cases, that actually require refactoring of the code for distributed computing. Now, most cases, the code that's designed in research is not fitted into production environment because of simply performance. People don't necessarily think about parallelism, about potentially incorporating caching technologies, so they don't just go and read the data on every request. Sometimes GPUs make a lot of sense, and we need to incorporate libraries for CUDA and maybe change our code to support GPUs and etc. But when we have a code which is scalable, performant, packaged, the next thing we have to start thinking about is observability, monitoring. But it's not just monitoring in the traditional sense of Kubernetes and microservices of CPUs, memory, etc. We need to monitor and log everything. We need to monitor the experiments that we're doing, the data that's generated with the experiment, the code that was used in order to generate the experiment, etc. Because there is a big portion of liability and explainability as part of every machine learning project. We run a project, we generate some results, we want to be able to go back to the same experiment, or we launch something to production, we had some issues with how we predict outcomes, someone sues us in a court of law, we need to be able to explain what we've done and what were the models and how we trained the models, and make sure that we haven't done any mistake in that. So the monitoring and the observability part in machine learning is much more extensive than what it is when you're talking about standard microservices. And the other aspect is security, of course. The security has many faces. There's data security, API security, role-based access control, access to credentials and secrets for external databases and services, and so on. And the final piece, in order to make this workflow not sort of a single or one-time flow, but something that can reiterate and go on and on, is automation. We're all familiar with CI/CD in the notion of computation and coding. We have to apply a similar approach of CI/CD and GitOps for machine learning. We need to build workflows that incorporate machine learning workflows. They're slightly different than our usual CI workflows because they require a lot more computation, and there's a lot more data involved in machine learning sort of workflow. This is really where Kubeflow comes into play, and we'll talk about it. And obviously, we need to think about continuous deployment, rolling upgrades, canary deployments, A/B testing, etc. Usually, this part from the development to productization is the biggest part in every project. So there are some companies where I work with them, and it takes them like 12 to 18 months with the original project to deploy into production. And it's very essential that we try and automate those processes. One of the technologies that we're going to show you how it's pretty significant can bring significant advantage is serverless, because this is essentially what serverless technologies in general do. They allow you to bring code, they automatically do the packaging, they have inherent scaling out, they do the instrumentation, and in some cases the automation. We need to add some other significant parts which are missing from traditional serverless, which are around performance and parallelism and data statefulness, and also more specific, tracking and observability for machine learning. So we'll see how those things take effect. So first, what is MLOps? Before we dive into an MLOps sort of presentation, we all know what DevOps is. Essentially, this is according to the traditional definition, is essentially combining development and operations to work together and try and solve the main business challenges. So MLOps is pretty much the same, just embedding all the aspects of data engineering and data science into the process. So it's not just developers and operations, it's developers, data scientists, data engineers, etc. They need to collaborate. And one of the key challenges is not everyone is a programmer or a DevOps guy in this world, because data scientists, they don't have necessarily all the software practices that and software engineers have. And we need to be mindful of that and try and simplify, not necessarily force YAMLs and Docker files on the data scientists, but try and speak their own language when we present them APIs and tools to work with. So before we dive into the solution, let's look at the typical use case. This is a use case that we've deployed on several places. There's also a Git repo that you can see here, which has the full example with all the services. So if we're looking at, this is a predictive maintenance pipeline. How would it look like? So predictive maintenance pipeline would accept data from two separate sources usually or more, like an operational database that gives us information about devices, entities, etc. And we may have streaming data, usually in the form of a Kafka stream that arrives and tell us information about like telemetry data, device updates, alerts, etc. What we need to do is essentially ingest all of that data, the operational data coupled with the streaming and transactional data, and throw it into a raw data bucket. Raw data bucket could just be a shared file system with Parquet files or CSV files. Could also be something slightly more structured, like a data warehouse. But the first thing we need to do is place everything in this sort of raw data bucket. The next thing we want to do is essentially start taking those raw features and convert them to something meaningful that we can run training on. So we may need to join various data sets to extend the knowledge. We may need to aggregate things into buckets of time, like hourly average number of events, what's the time from the last error to the recent error, and all sorts of what is referred to as features in machine learning. So it requires sort of a strong and high performance analytics capabilities. And then we have a new data set, which is usually a single table, unlike the source, which could comprise of multiple tables. Here we have essentially a single denormalized table, which is going in through a training logic. But even before going into a training logic, we need to sanitize those features. And if we have thousands of features, maybe we don't really need to train on thousands of features. Again, it's more computation power. It's going to have skew in the model if we're not going to learn based on the right features. So the next thing is to go and filter and auto detect what are the meaningful features and leverage those and maybe scale those to the right degree. Once we have those prepared features, we may need to go and run training, and the training will generate a model. This model will be later used for serving. But also before we use that model, we want to validate it using a different, smaller data set. We're essentially splitting the entire data to a training set and a validation set. And then we generate this model. We take this model and validate that it actually performs and what's the accuracy. If it doesn't, we may need to go back and forth and tune this entire pipeline. Now, once we have a model, we're not done. This is really what we've just covered is the model creation part, which is covered nicely with Kubeflow. with the extension of what we've discussed, essentially moving the individual steps in the pipeline to a reusable, high-performance, scalable function. We'll see the architecture in a minute. The next piece in the puzzle is essentially running serving, and so we take the data, we take the model. We can't just stay with the model. We have to bring data, because remember what the serving logic does is essentially takes a set of parameters, a set of features, and runs some mathematical functions and produces a result. So, and the request coming from the user doesn't contain all those features. So what we would need to do is essentially take data from some operational databases in real time and bring it into the serving engine. And this is usually done through some sort of an API service or an enrichment service, run it against the model, and respond back to the user. Now, once we've done that, we're not done yet. We need to monitor the behavior of our model through some sort of a tracking system. How do we know that our model keeps on performing and is accurate, or we want to be able to monitor maybe there's misbehavior in the performance aspects, maybe glitches, but also does it lose accuracy, or do we see different data than what we've expected? So all the data from the serving, which is also high performance, so this is streaming data, is going to go into other microservices that monitor the behavior of our model. And based on that, they may trigger events. They may write it to a time series database and visualize it in like Grafana. They may also record some data into sort of batches. And then there's another set of tools that may compare the inferencing logic or the inferencing data with real reference data in a delay. Let's assume we predict something, but in a day from now, we'll actually know if it happened or not, if our prediction was true. So we can compare our predictions with the real results. And this way you also have another way of analyzing if our model behaves properly. And if it doesn't, we can trigger something to fix it. Retraining, bringing on data, changing the logic of our serving ensembles, etc. So this is how usually you'll see that this pipelines work. Again, you can see that it's not trivial. And this is a predictive maintenance pipeline. It will be the same problem with other solutions. And if you add things like deep learning and neural networks, it may even get complicated. There are many applications where there's more than one model in a single application. So those things may get even more complicated. Okay, so before you tear your hairs out, the most important thing is you can start. You've seen there are a lot of different moving components in this system, and there are a lot of different software projects that you can choose from. But the right way is essentially to try and take an ecosystem which completes most of the building block in the puzzle. For example, if you take some tools that were designed for Hadoop, along with some tools that were designed for Kubernetes and some tools in a cloud provider, and they don't work with each other, you end up essentially doing a lot of integration by yourself. So one of the nice things here is that Kubeflow is a mechanism, or is essentially a framework. It's not too complete or comprehensive, but at least it's something that can glue a lot of other things around it. And this is part of the things I'm going to show, is how to extend Kubeflow with monitoring, with serverless functionality, with AutoML and other capabilities, and making it a sort of an end-to-end machine learning framework. Okay, so essentially what we want to show is a complete pipeline where we feed in data, we do data preparation, we accelerate the training, we deploy an application, we monitor the application. In order to do all of that together, we have to also have some baseline of data that moves around this entire fabric. So how would the solution look like if we're opening that sort of pipeline? So we need 3 layers in the solution. The first layer, we need data. The data need to have few attributes. First, it needs to be relatively fast, because we're not talking about archival data. We're talking about data in the move. We're building a pipeline. One microservice writes data, the other microservice reads data. If it takes too much time, we're going to have a delay. In many cases, we're doing distributed computing, like in training or sometimes in analytics. So we want to have shared data. We want all those things to work together and maybe shuffle some data around between those microservices. We need sometimes streaming data. We need some key value stores for real-time data. We may need time series data in order to log all sorts of metrics. So this is where we need data, and it needs to be fast, secure, and also versioned. So if we run multiple experiments, we can also go back into a specific experiment and see and reconstruct that from the data we have. The next layer is microservices. Okay, and those microservices, this is a simplistic view of those microservices we need. We need services that ingest data from ETL, from streaming, from scraping, from HTTP APIs. We need data preparation, so functions that will do analytics, whether it's batch or real-time or stream processing, to join, aggregate, split, and do all sorts of manipulations on data. So it's going to be ready for the training. Then we need to run training logic, again, with usually distributed frameworks, whether it's machine learning or deep learning. And here we may also want to incorporate something referred to as hyperparameter tuning. So run the same experiment on many different permutations. And we want to leverage the power of Kubernetes of scheduling lots of containers. So not necessarily all the permutations run on one container. We can run multiple containers. Each set of containers will run different set of parameters, and then converge or combine all the results to a single sort of best result. And there's also an aspect of AutoML, which is essentially running a variety of algorithms, not just parameters, and running all those in sort of a gang and choosing the best algorithm. Note that we always have to store all the data, because even though the machine chose one preferred algorithm, we may want to look back in retrospective and see which model performed how, and maybe even choose not only the best algorithm or the best model, but the 3 best models out of a list of 10 or 20. Once we have that, we need to run validation and then deployment. Now, each individual step is a microservice. So if we're going to essentially go and create a microservice and a Kubernetes deployment or a Kubernetes job for each one of those, we're going to run out of steam very, very quickly. So the general idea is, instead of going and running and creating Docker files and YAML files and Kubernetes CRDs and all of that for each individual step, we want to have more of a serverless mindset. We want to write some code, provide minimal description, and we want something else to build those services for us with the YAMLs, with the containers, with the Docker images, with the dependent packages, with the considerations around scaling and all the aspects of logging and monitoring. We just want to provide some code and let someone else deal with that. And this is really where serverless technology will come in very handy. And finally, when we have all those individual steps, we need to orchestrate them, and we want to create an end-to-end pipeline. And this is where Kubeflow and other tools are going to be useful. So a typical stack would look like something like that. So you have the data layer. Remember, we mentioned a lot of times we need real-time access from microservice to other microservices, from microservices to obtain features that are more require low latency access. At the same time, we need access to big data in the form of files, object store, data warehouses, etc. So we need to have a layer. In Iguazio, we have our own real-time multi-model data layer, which is serving file, object, tables, and other interesting formats in very, very high performance. And along with, again, object files, external databases. Then we have Kubernetes, and there are many managed Kubernetes options out there. And on top of it, you need all of those variety of services to make a comprehensive solution, and probably more that are not shortlisted here. Things like Spark and TensorFlow, and if you're doing SQL or something like Presto, and for machine learning, you need like scikit-learn and PyTorch, and Horvath is a way to distribute deep learning jobs, and Dask is a way to distribute machine learning, etc. And Jupyter is a managed notebook. So you need to install a bunch of services on your Kubernetes cluster and make sure they all work. In our solution, again, it's a managed offering, so you don't need to have all the hassle. It just works out of the box. We are suffering from the integration, not you. And then you have a set of tools for pipeline orchestration. Now, there is Kubeflow, and Kubeflow is mainly serve a graph execution. Kubeflow pipeline is a graph execution entity. It is missing a lot of other aspects that we need, like feature store, like AutoML, hyperparameter tuning is not really built into it, or and even experiment tracking. There are some challenges around how you do experiment tracking. You want to do, in many cases, experiment tracking not only within a workflow, sometimes just run experiment tracking on your laptop, and that's something you cannot do with Kubeflow. So you need another mechanism that can work with Kubeflow for tracking experiments, but also can work on a standalone machine or just running an individual step in the pipeline. So, and also we'll talk about the gaps and what we need to do. So this is really where another tool called ML Run is filling up those gaps by orchestrating a lot of the workloads and automating and making it really, really friendly to data scientists, not to DevOps or ML engineers. One of the key solutions what we recommend is working with serverless function, because we mentioned before that one of the biggest challenge is moving from code to like a production artifact with all the aspects of scaling, performance tuning, instrumentation, logging, monitoring, security hardening. So one of the ways to do it is essentially leverage code and to production with serverless technologies. And for that, there are several technologies that we're supporting and they're part of the open source. Nuclio is one of the sort of highest performance, very mature serverless framework over Kubernetes, more than 3,000 stars on GitHub, used by many enterprises. And there's also ML Run, which is more for batch computation, and I'll show how it works. So one of the major advantages of Nuclio, that beyond being a standard serverless, it's very, very high performance. It's using a real-time kernel. It runs about 100 times faster than things like Amazon Lambda. It runs about 10 times faster than most other serverless frameworks over Kubernetes, including KF serving and some of those. It's stateful, so it can actually work with data and GPUs and things like that in the function, which is very essential for machine learning. And also one of the nice things, it has glueless integration to Kubeflow. So you can essentially create a graph of computation where the individual steps are functions, essentially serverless function. And there is a marketplace where you actually don't need to write most of the functions for AutoML, for serving, for training, for data preparation, for feature analysis, for hooks to Git and Slack and things like that. So you just can put a bunch of components on a canvas and get a pipeline up and running very quickly. Again, one of the main challenges of serverless that it's very event-driven. So one of the things that we see is that we want the benefits of serverless, which is resource elasticity, automated deployment, automated operation, but we want to extend it to new workloads that are more like data preparation and training, where jobs can be tens of minutes or hours, where the way you scale or distributed the workload is not by load balancing or a service mesh, but it's rather through data partitioning, data shuffling, reduction, hyperparameter shuffling, things like that, which are different technologies. And also must be stateful, because if I'm processing data at scale, I have to have a distributed database or distributed file system as the anchor for moving data around between those individual containers. Another major difference in jobs and data preparation and training is, instead of passing JSON, as an event, we are actually passing data. We're creating a pipeline with parameters and data that feed each other. We have data set output of one step feeding a data as an input data set for another step, like data preparation, creating a data set, and training consumes that data set. And so we need to have a new serverless approach which has those attributes, and this is where we've created a new framework essentially just for that. So part of what we refer to as ML Run, which is open source, again, relatively new, but very, very powerful solution. It has several layers. The serverless engine is essentially one layer. It also has a lot of higher level automation layers. And so the general idea is that it auto scales. It allows it to do scalable computing over multiple frameworks. You can create a serverless function of Spark, of Dask, of MPI job. A lot of different CRDs are orchestrated by ML Run. So you can essentially create distributed computing, and ML Run knows how to break the work and control the distributed job, etc. Another interesting piece is that it has auto tracking features. It essentially knows how to look into the inputs and outputs of every execution and auto record that. So you get auto recording of all your experiments and runs and code and data inputs and outputs, etc., as I'll show in a minute. And again, it runs over multiple frameworks. Another interesting thing is, there are other frameworks for hyperparameter in Kubernetes, like Khatib and others, but then you need to manually go and integrate them. And if we have an engine here that knows how to run many different permutations already distributed, the only missing piece is having something that knows how to create those permutations and track them, which is actually built into ML Run. So you don't need a separate project for hyperparameters, and you all have AutoML built into the solution. So which is new. There's no AutoML solution on top of Kubernetes beside ML Run. Okay, now where does it fit? So Kubeflow is something that Kubeflow project has two main things, or three main things. One is a Kubeflow pipeline, which is this orchestration capability, and then you have the operators like MPI job or distributed TensorFlow and others, which you can also install by yourself. And there's also managed notebook. So, but the most interesting piece is Kubeflow pipeline, which is based on Argo engine, distributed workflow engine, and it allows you to essentially run a graph. The challenges with Kubeflow, it's very oriented towards DevOps. It's not designed for actual data scientists to work with it. And data scientists like simple things that are very, very simple. They don't understand Docker containers in many cases, or YAMLs, and they don't want to build JSONs that build artifacts for them like you would do in traditional Kubeflow. They want to make things very, very intuitive and simple in their own domain of expertise. So what ML Run and Nuclio provide is a way to essentially automate the code to creation of serverless functions from code. It delivers all the integration around data, access, and parallelism. It allows you to do distributed training, GPU acceleration, and other features that are not built in. And it does end-to-end tracking of everything: code, execution, data versioning, etc., all in a sort of in a graph that you can actually just play around and move around between the different aspects. So how does it all work? If I'm looking into it from a flow perspective, take this data scientist. What he wants to do is build something in his own notebook or his own PyCharm or VS Code. Still, he doesn't know Kubernetes or doesn't care about Kubernetes. So the first thing we want to make sure is that whatever we're building can work in a standalone. And that's part of the challenges with Kubeflow. If you want to run Kubeflow stuff, you have to run it within Kubernetes, and within Kubeflow, you cannot run an instrument and do the tracking and all of that from your notebook without Kubernetes attached to it. So the first thing that we want to do is essentially just import an SDK and allow someone to run from within his notebook and still get all the experiment tracking and all the data lineage tracking and all that done automatically for us. At a certain point, we've debugged our code and we feel it's ready for just running it as a container on the cluster. Still, we don't want to build and all of those things. We just want to say run, but this time on the cluster. So essentially just a single line saying not locally, but in the cluster. What it would do, it essentially automatically packages your code, throws it into the cluster, builds your containers, builds the CRDs for the various runtimes that are supported, like Kubernetes job or Spark or Dask or any of the other ones, runs it, and you still get the full tracking even while you're running this job on the cluster. Now note that at this we don't really need a pipeline. We just want to run a single step of, let's say, training. We want to test, validate, see that it works. And later on in the process, we want to turn it into a pipeline. So this, once we've committed our code into a repository like Git, then we want to take those pieces of code and just put them in a layout or a pipeline, and this way run the entire pipeline. So someone else or the same guy can just take all those components, build a pipeline, and execute that through Kubeflow or ML Run APIs. The other nice thing is that you don't really necessarily need to make it interactive. You can make it as part of an automated CI, just like you would with any other CI product. So essentially, you can commit something into a Git repositories. You put a hook in your commit repository, and I can show you a demo in a minute. We have a full-blown demo for that. So you commit something into the repository, then that generates a trigger. ML Run goes builds the entire Kubeflow pipeline for it, and it connects all the dots, the data, and everything. Runs the Kubeflow pipeline, tracks all the information about the pipeline execution. When the pipeline execution terminates, records everything, writes it back into the pull request as a notation in the pull request, and throws in a Slack notification back with a summary of your execution. So this way you can move very quickly from just developing some code on a notebook, testing an individual microservice, seeing how it works, running an entire pipeline, and even putting your pipeline as part of a complete automated workflow. And then if you were thinking about the entire process, what we have is, for example, we have a branch. We create a branch out of the development branch. We run some code locally in our environment. We convert it to a function using a single command. We test it on the cluster, see that it works. Maybe we're missing some packages, or maybe we misconfigured something. We go back, fix it, and that's we're done with the development. The next thing is we need to think about integration. We're trying to pull request that change that we've made. This change goes into some inspection. We can have automation in most Git repos of like examining the Python code, Flake and Blake and all of those tools. You can write some of your own test scripts. Once it passed the basic tests, we want to run a complete machine learning pipelines using Kubeflow. So this is where we can just integrate that with pull request command, pull request comments, as we've done, and then once the pipeline runs and you get the accuracy and you get everything, you can merge the pull request and even request for a deployment. Once we finish the integration, we want to go and run the continuous deployment. This is where we may create a tag of our repository, deploy the models and the code that goes along with that. That may be feature engineering and some other aspects. Deploy that in a canary. Once it's working, we've examined it, everything is well, we're going to promote that into 100% of the traffic and keep on monitoring the service behavior, concept drift, etc. So this is usually one of the ways of implementing that. To tell you that most organizations already work in this way, it's sort of still evolving, but the ones that have managed to move into this process are becoming more agile and can drive a lot more work with less people. So that's with that, and this brings a lot of value. So people can build pipelines much faster, and the pipelines could be more interactive, more online. One of the examples is this work with one of the customers that we've done is take for a fraud prevention application. The original solution was using Hadoop, where you have a database, you extract everything using ETL into a data warehouse, you run some queries on the data warehouse, and then have R servers and doing prediction using an R model and writing back, identifying the fraud accounts and blocking those fraud accounts. So this process is very batch-oriented, very manual, very complicated if you've worked with Hadoop and all of those frameworks. And instead, we want to move it into microservice architecture, which will buy us two things. First, faster deployment process. Everything, instead of 3-4 months deployment for every change, it could actually be continuous, or every week or a couple of weeks we can drive a change. The second is we don't want to have such a huge delay because everything is like batch oriented. We want to move to something more online. So the change that we've applied is essentially to gather the information from the server, the database server, directly as a stream. So you run serverless functions using Nuclio that essentially crunch the stream in real time. Nuclio listens on about 13 different streaming protocols: Kafka, Rabbit, Kinesis, PubSub, etc. So you can just listen on Kafka or Rabbit in this case, do real-time analysis because it's stateful, again, so it can do things like real-time analysis of data, write it into combined online and offline feature store. You can also run things like Spark to do batch analytics on that feature store and extend the features even further, looking at a bigger retrospective or bigger time window. And then periodically, for example, on a daily basis, you have a model training process using scikit-learn that extract a feature set, a training set of a bunch of features, run the training, generates a model file, and then you have inferencing function, which in this case, they have to work in a stream because there's no HTTP request. The data which is written is essentially generating a stream, and that stream is consumed by the inferencing function, which identifies the fraud, and then just based on the fraud, just blocks the account. So in this process, we've taken a process that was 40 minutes to identify the fraud into more of a continuous pipeline, which knows how to identify fraud within 12 seconds, so significantly faster, a couple of magnitudes faster. But the other main advantage is that each one of those steps here is a microservice or a serverless function where in order to deploy a new version, the only thing I need to do is change a little code and push deploy, or go to an API call and say deploy, or even through CD, continuous deployment tools, just do the deployment automatically. So this way, we are much more efficient. So with that, let me show you a short demo of how all this thing is really running in reality. Okay, so let me share my screen. Okay, I hope it's visible now. Okay, so what I'm opening here is a notebook. This notebook is going to show me how I can build a full pipeline. So this pipeline, it's all fully documented. But the general idea is I have a function. In this case, again, we said we want to take those jumbo notebooks and try and construct them in a way using sort of functions and not just like straight code. So I have some function which is generating some fake data set. This is using the iris data set. And once it finishes, we want the function to log a data set, to essentially log an artifact of type data set, essentially a data frame. And this logging effect will essentially record everything in a database, track lineage, track statistical behavior of the data set, and all those things behind the scene. So this context event that's part of the function execution can carry many different things. It can give us access to secrets and other things. So at a certain point, we also may want to package all those functions under a logical project. But then what I need to do is just execute this function. Now I can just go and execute this iris generator function myself, but what we're doing here is we're running it under a wrapper that runs the execution. It's running our function, essentially wrapping it up. Why do we want to wrap the execution? Because we want to record everything that goes in and goes out into the function into a database. And you can see that once I'm running this function, I also see some nice widget that shows me that it ran, the name, how long it took, and a bunch of labels, even what I can actually see the data that was generated by that function. Okay, sorry. So I can just run, and this generates a data set, the iris data set. If I really want to see that data set also and track it, I can also click the URL. It will open a separate UI for it. The next thing we want to do is we'll register that. We'll convert it into a microservice. Essentially, I promised you a single line of code. So there is a single line of code that converts my code into a function, essentially into a microservice, into a serverless function. Now I have a function object I can use, for example, register that in my project or do other things with that. Now I generate some data set, and now I want to take that data set and run analysis against that data set. So I may write a code for analysis, but then I need to package a new container and put a lot of libraries in it and build YAMLs and Docker files. Instead, I can just go and grab a function from a marketplace called describe, which is running analysis on my data set and is showing me the behavior of each one of the features of my data set. Because I don't really know how it works, I can just ask for documentation. I'm going to see the full documentation of that function. And now I want to run this function on my data set. So I have a data set that I just generated in my notebook, and I want to run something that analyzes the data set in my notebook. So in order to do that, I need to run this function called describe. Because I wanted to analyze data from my notebook, I need to mount it over a shared file system. So the notebook and the job will see the same data. So there is something in Kubeflow called modifiers, and this is using R cluster file system, but you can also use NFS or PVC in order to share data between different containers. And then I want to run this function with a set of parameters and inputs. So I want an input of my data set, the ones that I just generated in my notebook, to be used as an input for this task, for this analysis task, and I'm running it. Now this time, there's a magic here. It's actually not running on my notebook, although it looks like it's running on my notebook. You see it actually allocated pods to run this job, and also responded with a bunch of interesting results. So I can just go and look in my directory. Remember, it's a shared file system, so everything lands back into my own directory. And I could just go and look at all those nice charts which were generated by this analysis job. So I can look at the histograms of the data. I can look at the feature correlation and all those things. All this analysis doesn't have to burden my own container. Another nice side effect is that those containers are allocated dynamically, so I don't have to have upfront sort of payment on those VMs or containers like in many services. The resources will get allocated dynamically, and if I need GPUs for those services and I register as part of the requirements, it will automatically allocate the GPU and deallocate the GPU when it's done. So it's very important. It saves a huge amount of cost. Now, after running this, I want to create a complete pipeline. A pipeline comprised of classification logic, essentially training, and then validation logic. Then I want to deploy a service, the endpoint, the serving function. And once I deploy the serving function, I want to test that serving function to see that it has the right performance, latency, etc. So I can just go and pick a bunch of those functions already from a library. You don't need to write them. By the way, it's all open source. It's part of there's a Git repo hosting all those functions for AutoML and data engineering and others. And now I create a Kubeflow pipeline. So this looks like a Kubeflow pipeline. The main difference is that instead of having a Kubeflow pipeline of Kubeflow operators, you have a Kubeflow pipeline of serverless functions, which are automatically converted to like a Kubeflow pipeline operation. So I'm just going to take those individual functions that I have. I can have build functions. I can do an analysis function, again, ingestion function, analysis function, a training function with AutoML, which runs all those variety of protocol algorithms. And then I need to have a validation function that validates the output model and the testing set of that model. And finally, I want to deploy a serving function. So it's not just for the training. I can actually build a real-time pipeline using this engine and I can test my real-time pipeline with another. So I incorporated data engineering, machine learning pipeline, and CI pipeline all in a single workflow. And then I just run this simple Python code here locally, and I see all the results of the pipeline once it's complete, brought back into my notebook. I actually don't have to go into Kubeflow and examine the results, although I can just go and see all those results in Kubeflow. This is part of our managed platform, but any other Kubeflow also works. So the other nice thing is that all the artifacts are automatically recorded. If I go to the training, I see all the artifacts which the serverless function generates automatically recorded. Also for the data analysis and all those nice widgets. And this is where it actually deployed the Nuclio function for real-time serving. And then we use the tester to test the performance of that serving function. So we can actually see the latency. We see that it's around 11 milliseconds. So it's really decent performance. Obviously, we haven't tried to optimize here or anything. So you have the full control. Now, all of those things that I did are also recorded in ML Run. So I can just go into this UI, and ML Run doesn't care where you're running the job, whether it's running in Kubeflow as a separate job within the notebook. It sees all the variety of jobs. They can be grouped by name or by Kubeflow workflow. And then I could just go and look into each one of those jobs. We can see what's running. We can actually see the code, commit of that code, and see the actual code if we want. We can look at all the artifacts that were generated in each one of those steps. We can look at the logs in real time. This one didn't really have a log. Let's move to the training function. If the training functions include AutoML or hyperparameter tuning, you can actually see all the individual results, and then it auto-selects based on your criteria the best result to move into the next step of the pipeline. So the AutoML and the hyperparameter tuning is built into this framework. You don't have to go in and use another framework just to get this thing. And also you have a way to manage everything, the functions, the artifacts, the jobs. There's going to be a new UI very soon, and again, everything is on GitHub. The other important thing is those functions which I generated. Nuclio is not limited to HTTP. You can essentially go and add any trigger you want, Kafka, Rabbit, Kinesis, cron, whatever. You can configure a lot of things like the resources, auto scaling, minimum, maximum, secrets, volumes, everything that you can think of that Kubernetes can do could be abstracted using Nuclio. And again, this function was actually generated from a notebook. I have a notebook here, this serving notebook. See this function, which I can write in a notebook at just when I feel I'm ready. After I tested this notebook, I have one thing to do. You just say function deploy. This will automatically create the function for me, or taking that function and embedding it as part of a complete workflow. Another cool thing about those functions is Nuclio also supports API gateways and canaries and all those things. So you can go and create a gateway, a new API gateway, which allows you to authenticate an endpoint and create canaries, assign multiple functions and give different percentage to each one of the functions. And by the way, all the things that we monitor are also written to Prometheus and Grafana, all the statistics of functions, jobs, everything. So think about how much work we've saved you with those serverless frameworks. So all the logging, monitoring, all the auto scaling, regardless of how you want to scale, whether it's Dask or Nuclio or Spark or any other architecture. All the tracking with all the linkage of all this tracking and artifact and job, all of that is fully automated. So that means that you can turn project that could have been consuming tons of DevOps and developers and take months, you can just implement the same project within weeks. And everyone will be happy because you have all the instrumentation, the best performance you can think of, etc. And so with that, that's my session. Welcome any questions or comments. You can also find me in LinkedIn or Twitter, and I'm happy to talk to any one of you if possible.